Hope you like it. Hey guys, it's time to zone in here and make sure you got this. Make sure you're paying attention. So I've drawn this graph for you. Bless you. And I'm wondering if any of you have any guess as to what sort of relationship or equation created that graph. It's pretty obvious, right? Y equals X. You guys, I mean, that was what half a dozen of you said. That makes sense? So then, you know that that's shaky ground, right? Just looking at a graph and be like, I think it's this, or I think it's that. Because depending on which part of the graph you're looking at, you could be deceived, right? Can you think of a way that you could confirm that, yes, in fact, this is Y equals X?
Take the derivative right where you are.
Stay right where I am?
And take the derivative.
And take the derivative. What do you mean? I don't have, like...
He was confident, that's all.
I guess what I would say is the derivative of what?
That graph should be 1.
Okay. And so I look at that, and so I mean, I don't have a square window, but does it look reasonable that the slope of that graph is 1? Does it look reasonable? Could someone look at that, and could you see how somebody could look at that and say, yep, looks like the slope is a constant 1. I'm down with this being Y equals X. So can you think of a different way that would maybe confirm a little more strongly, or maybe even deny that this really is Y equals X? Another point. So how would I get another point that's on this graph? What would I need to do? Scroll? You mean like trace?
Yeah.
Trace. Okay. So if I go, not second, if I go just trace, okay, and so start moving around. Find another point. Okay. So I'll move around a little bit. So I just scroll to the right slightly. So what's the significance of the X and the Y coordinates matching? Fits the Y equals X pattern. And so this is kind of Johnny's idea of, hey, we got the 0, 0 thing going on. Let's get a second point and calculate the slope, right? And what's true of a nice straight line like Y equals X? What's true about the slope? It is 1, right? Like no matter where you are on the line, the slope is 1. So what should I be able to do with my little trace feature to like really for sure prove that the slope is always 1? What should I be able to do with the trace? So far, all I've proven is that the slope between 0, 0 and that point, I've been able to prove, it appears at least, that the slope is 1, right? I should be able to prove it for every point. So let's try that. I'm going to keep scrolling around here and just see what happens. So pay close attention. What do you think about that point? We good? Still looking like Y equals X, right? Good? Don't zone out on me here. Still feel okay about this? Y equals X is our equation. Anybody wondering anything? Any comments? I'm zoomed in pretty far, sure. Well, this is looking like, it's looking a lot like Y equals X, right?
Oh, wait, no, it's not okay.
Could this just be some calculator glitch because I'm zoomed in so far?
No.
Let's keep going. Let's keep going. Oh, hey, we're back to Happy Land. So maybe that was just a glitch. Yeah, let's just pretend like that never happened. Yeah. Well, I don't know. This. Oh. Whatever it is, like 1/10 trillionth or something, right? I don't know. Oh, we're back to Happy World.
No, I think we all agree to
So you have an issue? Do you see how the X and the Y don't match here? Huh. So what do you think? Is this just because... we're back to the better place now. But now we're not. Your dog is slightly off the screen, Josh. I'm sorry. If we just scroll far enough, we'll get there. Sorry. It's not a farm in the country. You guys see how... You see how our happy place is less and less common? So, yeah. Can anybody describe... There's a pattern here. Can anybody describe the pattern that's starting to emerge? But that's not true, though, because this point didn't match either. This point, they don't match. So it's not really every other point. Like, for a while, it was like match, 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 didn't match. Match, 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 didn't match. And then it seemed like it was kind of every other, but now it's like 2 in a row don't match. What's the pattern? It's not random.
Is it like the opposite? Because on that one graph where it converges, this one's like converging on opposite directions.
I think your use of the word converging is pretty interesting, for sure. I'm not sure what you mean by opposite directions.
Like in both ways. Like, because like it's one here, then here.
Yeah, the whole like alternating thing. Interesting. Very interesting point. I think we probably could see an emerging pattern in that regard. There's a different pattern I want you to see, though. Let me keep going. Maybe you'll see this better. So, guys, remember that. Let me just highlight something real quick. Remember that when I was tracing, like in this general area, the X and the Y matched every single time, right? But then I started to get over to here in this little green area. And that's where it was like we started to see some X and Y's that didn't match. A little less frequent. And then like right in here, in this purple section, it seemed like it was just about every other one. It was like match, didn't match, match, didn't match. It was going back and forth. And now finally where I get to where I am here in this red area, I guess I've got 2 red areas. Let's go with this orange area. And this orange area over here, for the first time I got like a couple in a row that didn't match, right? Colin?
As X gets bigger,
There's more influence.
No, I said in frequency.
Oh, in frequency. I thought you said influence.
Fluctuations of the...
Fluctuations. So I get it. No, I get it. So he said, as X gets bigger. And I kind of agree with that. I think we can say it a little bit better. How could we... Say again? Increases, gets bigger. That's kind of the same thing. You said approaching infinity.
It's further away from 0.
Okay. That's, I think, going to be the best way to say it. I started at 0, 0, right? Everything seemed to match. And the further I got from 0, and let's keep going real quick. The further I get from 0, notice this now. Now they never seem to match. Do you see it? I'm getting further, and I'm still, you got to admit, I'm still pretty close to 0. My x-coordinate is basically 5 1/1000ths. Right? So I'm still pretty close to 0, depending on what your definition of pretty close is. But the further I get away from 0, the consistency of the discrepancies showing up gets more and more, to the point now where none of them match, right? Yeah, nothing seems to match. So earlier, like 9 minutes ago, based on the information that you had, you were all fairly convinced, yep, this is a graph of y equals x, correct? Now how do you feel? Of course you had some doubt in your mind, because why would I show you this? You're suspicious, I get it. have we confirmed that this is very likely not y equals x? I want to get back to what Colin said, though, guys. Today's discussion is going to be full of these awesome little sound bites that later on, as we move through this unit, you're going to be like, oh, that's what we did on day one of this unit. This makes a little more sense now. So I hope that you'll try to glean as much of this. Feel free to write any of this down. Mostly I just want you to absorb and participate and think. But I think you'll notice some of these things will like weave their way right back in. We're really laying the foundation for everything we're going to do in our upcoming unit here. Okay? I want to go back to something Colin said. He said, the further you get away from 0, the less this looks like y equals x. Right? If you get further away from 0, this looks less and less like it's really y equals x. Easy for me to say. So you want to see what this really is? Anybody have any ideas?
Sign of X.
Let's find out. I'm not going to do any magic here. I'm going to push 2 buttons. Zoom 6. This will get me to a standard window. Let's see if you're right. Zoom 6.
Hi there.
What does that look like?
Cosine.
Oh, you were right. It's sine. Y equals sine of x. Pretty cool, huh? Can I show you how that was made? It's super simple, right? You just zoom in. So I'm going to go zoom to, enter. I'm just on the origin, right? So can you start to see that y equals x showing up a little bit? Zoom to, enter. After just 2 zooms, it's already sort of kind of looking like y equals x, right? You can still see some wave to it. Zoom to, enter. And I think to create the one that I made for you, I might have hit zoom to, enter like 2 more times or something like that. But even after just like 3 or 4 of these, this looks a lot like y equals x, doesn't it? So, some key takeaways here before we go through this little process. I think this will be super fun. Around the origin, you got to admit, even after we traced it, wouldn't you have to admit that around the origin, y equals x is a great approximator for sine? Would you agree with me? Let's look at it. Let me go back to Zoom 6, and there's our sine graph again. So I'm gonna go to another equation here. So I'm just gonna enter y equals x, and this will be in red. So here's that graph. So take a look around the origin. We're zoomed out fairly far here, but can you see that like around the origin, that red line is quite a good approximator for the sine curve. In fact, what would you guys call the red line? It has a name. Calculus student. Beyond that, what kind of a line is it? Isn't it a tangent line? In fact, this would be probably a worthwhile exercise. This is something you've done a million times or close to that. If I wanted to find the equation of the tangent line for sine at the origin as the point of tangency, let's think about that. My point, remember the 2 things you got to have to write the equation of any line are the point of tangency. And wouldn't the slope be y prime equals, what's the derivative of sine? Cosine. So then y prime of 0 would be cosine of 0, which would be 1. Well, what kind of a line has a slope of 1 and a y-intercept of 0? So that red line is the tangent line at 0, 0 to our blue curve, right? Okay. So I'll get rid of that stuff. Okay. Do you guys remember, gosh, it's been a little while since we covered this. We'll cover this again when it comes to like AP review time. Do you remember how we've done questions like this in the past? Step 1, find the equation of the tangent line. Step 2, use that tangent line to approximate the curve's value. Yes? And then step 3, tell me, is the line's value an overestimate or an underestimate of the curve's value? Right? Remember those questions? And you had to give a reason for your answer, justify your answer, that kind of thing. Yes? So would you agree with me that, like Colin said, that close to 0, 0, the line was a really good approximator for sine, right? But the further you moved away from x equals 0, the worse the line's relationship was as far as approximating the curve. That's because 0, 0 is the point of tangency, right? The further you get away from it, the worse the approximation is. So I have a proposition for you. Let's see. Now let me write something down. Do I want to do this? Yeah, let's do this. So if I said something like this, how about y value of the curve, like the real true y value on the blue graph, is equal to the y value of the line plus some error. And maybe we know the error, and maybe we don't. Wouldn't we acknowledge that the line, other than at 0, 0, the line is going to be off from the curve by some degree, and that degree would be the error, right? So if I knew exactly what the error was, I could say that the actual point on the curve is equal to the point on the line plus whatever the error is. Okay, so then let me rearrange this a little bit. I'll let you do it. How could I quantify, how could I express the error? How could I rearrange this so that the result is the error? What would I do, Johnny? Y of curve minus y of line equals error. Does that make sense? So let's do this. Let's see just how bad the error is if I use the line to represent the curve. Make sense? So here's what I would do. On my calculator, I'm going to go back to y equals, and I am going to, we've done this before, I'm going to turn off the graph for y1, and I'm going to turn off the graph for y2. So like when I hit graph, these won't show up because I just turn them off. I turn the equal sign off. But down here, what I'm going to do for y3 is going to be like my error expression. So I'm going to say y3 is equal to, oh, I didn't want to do that. I'm going to go y1, let's go to here. I'm going to go y1 minus y2. So would you guys agree with me that y3 will give me an expression on the graph for the error comparing the line and the curve? Does that make sense? Sir? I'm not going to get too concerned about that right now, about the over-estimate. I just wanted to refresh your memory that we do talk about that there is an error. Let's not worry about that too much yet. Let's just see what this does. Okay, so I want you guys to look carefully. So what I'm about to show you is the error, the expression for the error. So hit graph. Interesting graph, right? You can see the periodic nature of it. Obviously, there's a pattern to it. But what I want you guys to focus on, remember, we're looking at what's going on around 0, 0. So what I want you guys to look at is basically this domain here. If you kind of ignore the whole graph except for what's in the little picture that I've drawn for you, I want you to think, like, what kind of a function would make a graph like that? Cubic. What kind of cube? Negative. Yeah, one with a negative lead coefficient, right? So here's what I'm thinking. If I went back to my y equals, now please keep in mind what I'm trying to do here is think about how could I improve upon this tangent line thing, right? Because we know the tangent line is off. And so what I'm trying to introduce you to the concept of is, what if we took that tangent line and tried to modify it so that there was less error, right? So let's think about it like this. what if I came up here and said, you know what, I'm going to turn these two back on. So y equals sine x is back on the graph. This is back on the graph. But what if I wanted to improve my approximation? And we just said, you know what, the error looked a lot like a cubic, at least around 0, 0. So couldn't I take that error and add it back to my approximation, and wouldn't that reduce the error? Maybe even take it away? So the suggestion was negative x cubed. So I'm going to go minus x to the third. Now keep in mind, I turned the error off. The blue graph is sine. The red graph is my new thought for my approximation. Like, maybe this will make it a little better. So let's see what the graph looks like. So we're on the Zoom 6 window here. Of course, there is sine. And there's the approximation. Interesting, right? What do you notice? Is this better, worse, the same as far as like the red graph approximating the blue graph? What do you think? What do you notice? Very close.
I'd say it's worse.
Why would you say it's worse?
Because when we did y equals x, it almost went to like the x equals 1 point in terms of matching, but this is sort of stopped matching around like y equals x.
So Josh brought up, I think, a pretty important point in that before, when we just had y equals x, it seemed like the blue graph and the red graph appeared to converge, at least on this window. They appeared to converge from about -1 to 1-ish. And can you see, and I think this is Josh's point, now that interval of convergence seems to have gone from this to this, right? What else do you notice? Say again? Okay, yeah, within the smaller domain, it's better. Maybe, okay, very well could be. What else do you notice? What do you notice about the shape of the red graph now versus the red graph a few minutes ago? Now the red graph. Say again? What does the red graph have now that it didn't have 5 minutes ago? Is the red graph any different than it was 5 minutes ago?
Yes.
How is it different? It's got curves. It's got curvy features as opposed to just straight line. You see anything about those curves on the red graph that might be helpful in trying to match up with the blue graph? What do you see, Matt?
It kind of matches the concavity of the blue graph.
Sure it does, right? So like, yeah, I agree. Like the blue graph is concave down there, concave up there, and then of course you can see the red graph, you know, here and here, certainly does appear to have the same concavity, but there's a severe lack of matching, right? How would you describe like the relationship of the matching of the concavities of the red graph with the matching of the concavities of the blue graph? Like, how do they relate?
Blue graphs are wider.
Yeah. The blue graph, yeah, those curves, although concave down and concave up correspondingly, certainly wider than the red graph. So, my question would be, how, I'll get out of this real quick. How do you think we could widen out the red graph so that maybe it would better match the blue graph? What do you think we could do?
Divide it by...
Divide what by what?
Divide x cubed
Okay. Divide the lead coefficient by 9?
by 3 factorial.
3 factorial?
Exactly.
What an odd thing to say.
So 6.
Okay, so let's do this. Let's start here and do a little comparing. You'll just have to remember this. And we're going to see if your suggestions are effective or not. So I'm going to say that my interval of convergence appears to go from there to there. Do you guys agree that the red seems to totally cover up the blue on roughly that narrow little interval? So if we do this right, those two green lines would hopefully do this to some degree, right? Okay, so let's see what happens. Oops. So let's go back here. So Alex was the first with the suggestion. He said, let's divide x cubed by 9. So you guys all okay with the idea that if you divide the lead coefficient by some number, like 9 or as Josh suggested, 6, it'll widen out the graph, right? If you were, by comparison, if you were to multiply by like 10, it would skinny the graph, right? If that's the right way of putting that. So we said divided by 9. Let me hit graph, and we'll see, of course, there's our sine graph. Now, if you're not familiar with that before, you are now. And there's the red graph. Well, that certainly made a difference, didn't it? That made a pretty big difference as far as the way the graph looks. Let me see if I can mark that interval of convergence again. I would say now it looks like it's from right about there to right about there. So it has gotten wider, so that's good news. What do you guys notice about this? Do you think that this was like dividing by 9? Do you think that was the right number, or is there maybe no right number? It's just like kind of a matter of doing your best? What do you think? Should we try Josh's idea, or is this good enough? Or yes?
Let's try Josh.
Yeah, let's go with
Try
Josh.
Josh's number. Okay? So remember this as best you can. I would say that the interval of convergence goes from like, what would you say, like negative 0.8 to positive 0.8? So let's see if these other numbers help or hurt. So we'll go back here and we'll say, instead of divided by 9, we're going to say divided by 6. Here's the new version of the graph. You get to decide, is this better or worse or the same?
Oh,
What do you think about that convergence interval where the red matches the blue, or at least appears to?
it was pretty cool.
Is that better? Is divided by 6 better or worse than divided by 9?
It's better.
It appears to be better. I agree. So if you look at the interval of convergence now, it appears to go from about there to there. Whereas before it was like plus or minus 0.8. Now it's like plus or minus 1.2 or 1.1. So what do you guys think? So 6 is clearly better than 9 in that regard. What do you think? Is there maybe a better number than 6?
3 factorial.
Well, that's the same thing.
But it's 2
2 pi? Slightly bigger than 6? That would probably be pretty hard to tell, right? It's 6.28 versus 6. And so, yeah, are you guys settled? Do you think 6 is best? You think 6 is best? 6 is best. That is correct. 6 is best. At this point, there could be all kinds of questions of like, why? Like, why on earth would that be best? I'm going to reserve some answers of that for a little bit later. But for now, let's just say dividing by 6 on that is best. But, got to admit, that's a pretty narrow interval of convergence, right? I mean, it's barely bigger than plus minus 1. How could we make this better? What do you think, Dylan?
I was going to say, instead of 6 being the best, would it be like pi factorial being the best?
It is. 6 is really the best. It really is. With factorials, it has to be integers, or whole numbers, really. It can't be pi factorial. Although, that, I mean, you could be forgiven for thinking that that would work, because pi is a really important number, right?
Oh yeah, just because like the chart doesn't
Yeah.
intersect it for you because of pi.
Yeah, no, I get it. We could go around and around with that before we like settled on, okay, I think 6 might be best. Let's just, to save a little bit of time, let's say 6 is best. But I could still make the overall red graph better, right? Because, I mean, seriously, it's only decent from negative 1.1 to positive 1.1. Let's find an error. Let's keep going. So check this out. What if I went back and I said y equals, and I turn off my sine graph, and I turn off my approximation, and I turn on my error. And this is, remember, the error is where we got the whole x cubed thing, or negative x cubed thing to begin with. So let's see if we can figure out what this error looks like. So the error is on So what does that look like? What do you think? It can't be x to the third, right? Because if it was x to the... somebody, can you see how somebody might look at this and say that it's positive x to the third? It can't really be that, because then when I combine my like terms, wouldn't that just like affect the thing that I just made? Which we already decided was pretty decent, which you just totally changed. That wouldn't make any sense. Hope you guys understand that odd powers of x can sort of all look the same, more or less, depending on how zoomed in you are, what your window looks like. X to the fifth would be reasonable here. So let's do this. And if it is x to the fifth, wouldn't it be positive x to the fifth? Okay. So I'm going to go back here, turn this back on, turn this back on. I'm going to go plus x to the fifth. And we're going to turn our error off. And here's a graph of sine. And then in a second, you'll see the red graph, which is our approximation. What's happened? What do you see? What do you see as compared to what we just did? It's worse. Our old interval of convergence was like negative 1.1 to 1.1 roughly. And now it's back to like negative 0.8 to positive 20, right? It's a major issue. What do we need to do? Say again? Yeah, widen this thing out big time. So how do I take some polynomial like the red graph and widen it out? Divide by something, right? Love it. I love it when you guys pick up on it. It's good. I do. I do a similar exercise every year when I get to this point, and sometimes it takes a really long time for people to figure things out. Other times not, like today. So Matt, say a little louder. You decided we should divide x to the fifth by factorial. Okay, we could go with 120, I suppose. I'll honor the factorial concept with actually putting it in there. Okay, so then I've modified my red graph. Now I graph the sine curve as well as the red graph. And wow, look what happened. Just dividing by this magical number. That red graph, that looks pretty good. So remember, last time when we were up to cubed, we found out that our interval of convergence was from like negative 1.1 to positive 1.1. Now it stretches quite a bit wider than that. It goes from almost negative 2, right? Just about negative 2 to positive 2. So if all we did was zoom in on negative 2 to positive 2, you'd have to say, man, the red graph and the blue graph are almost the same. Really, really good. Let's do one more. You guys are obviously starting to see the pattern. So if I want to look at my error, I would turn off that, and I would turn off that, and I would turn on y3. Here is a graph of my error. Now this will be a new error. What does the error maybe look like to you? It's certainly not an even power of x, right? Because don't even powers of x have the same end behavior? They both go up or they both drop down. This is obviously an odd power of x. And adding x to the fifth makes no sense because that's just going to combine with the previous term. So x to the seventh certainly makes sense. Would this be a plus x to the seventh or a minus x to the seventh? It's decreasing, yeah, so minus x to the seventh. So let's go back and turn this back on and turn this back on. We're going to go minus x to the 7, and we'll turn off the error. So now hopefully this is better. We hit the graph. What's that? Oh, yeah, jumped ahead here. So do you see how, once again, by just tagging on a minus x to the 7, just like in the previous steps, we've messed this up, right? The interval of convergence doesn't even stretch out to plus minus 1 now. Clearly, we need to take our red graph like we did before and widen it out. And like before, the way that you widen out some polynomial is you take the lead term and you divide it by something. The suggestion is 7 factorial. I mean, I don't know where you guys are getting this from. But I would say, are you starting to see a pattern? I hope you are. So we're going to say minus x to the 7th divided by 7 factorial. And now be prepared to be wowed and amazed. Here's a graph of our sine curve and then our red approximating curve. Wow. Look at our interval of convergence stretches almost all the way from -3 to 3. So it seems like every time we tag on a term and we get the right term, that interval of convergence goes from here to here to here to here. It gets wider and wider. And you can see that, man, almost a full period of sine, the red curve is a really good approximator for sine. So it's at this point where we have to jump off a little bit and say, well, what's the pattern? How could we, let's just discuss conceptually, how could we make this better? Add x to the 9th over something and maybe it would be 9 factorial. What if that was not good enough? What would the next term be? Minus x to the 11th over 11 factorial. So if you look at the pattern within y2, you can see that it's essentially, I hope you notice this, it's essentially x to the 1st over 1 factorial, minus x to the 3rd over 3 factorial, plus x to the 5th over 5 factorial. You can see that the exponents and the factorial division match, right? Did you also notice that, especially if you watched the video, I hope that you did you notice that there's an alternating pattern within the terms? Plus, minus, plus, minus, plus, minus. Yeah, -1 at the end, depending on where you start your sigma, right? So how many terms, listen, what if we were totally disinterested in having any error at all? What if we said, I don't want there to be any error. I want my y1 minus y2 to just be 0. How many terms would I need to make that happen? Infinity, yeah. Did you notice this? Hang on. Let me show you this. If I turn off y1 and y2 again, I'm just going to graph the error. Please look. What do you notice about the error here in regard to the graph and having like an error of 0? You see how this appears? This is the error, right? This is a graph of the error. Do you see how the graph of the error at least looks like it's 0 for a while? So check this out. Like from -3 to 3 roughly, the error appears to be really close to 0. What if I did go back here, like you all suggested, and I said, let's make this y2, let's add a term onto it, because we said you'd need an infinite number of terms. I can't do that, but I could go plus x to the 9th divided by 9 factorial. Guys, check this out, please. You have no idea how rich this is. Later on, you'll be like, that discussion was really, really rich. Hopefully you'll get it now. So I just added an extra term. I want you to notice I'm graphing just the error. And it'll show up eventually. Oh, I must have turned something else on. The black graph is the error. Do you see how the error appears to be 0. Now from -4 to 4. So think about this. If I kept on adding terms, wouldn't the 0 error go from here to here to here to here to here to here, so on and so forth? So the more terms I add, the longer stretch of 0 error I get. Another way to look at it is the more terms I add, the better the red graph and the blue graph actually match up. Does that make sense? Okay. So what we're talking about here is something called power series. And the truth of the matter is, we're going to find that power series can be great representatives and or approximations, depending on the particular power series, of just about any function. Right? So what you guys just saw here, the x minus x cubed over 3 factorial plus x to the 5th over 5 factorial, dot, 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 right? That is the power series for sine with a centering point at 0. Didn't we start everything at 0? The truth is we can move the centering point wherever we want. 0 will be a very common centering point. We can move it wherever we want. And of course there would be other power series for other functions. So if you flip back to what was in your video, you've seen some of these. So do flip back. If you've got your notes in front of you, I think maybe I'll do the same thing. Where did it go? There it is. So if you take a look here at these, the ones that we kind of played around with right here. Do you all see number 5? What is number 5 describing? Sine of x. It's actually a power series for sine of x. This one right here, number 4, is something else. It's actually the power series for cosine. I'm going to skip number 3 for now, and I'm going to skip number 1 for now. Those are strategic moves on my part. You'll understand maybe later. Number 2 is also a power series. That's a good guess, but no. It's actually e to the x. Number 2 is a power series for e to the x, centered at 0. What you're going to find is this. For those, I'm really previewing the unit right here. Like the whole today is all about previewing the unit. Numbers 2, 3, and 4 there, you would find that if you keep adding terms, the interval of convergence does this. So we add a term, the interval of convergence jumps out wider, and then wider with each additional term, right? But you will find with other series, other power series, like number 1 and number 3, there are going to be certain cases where your interval of convergence starts off here, you add a term and it goes here, another term here, then here, then here, then here, then here. And after a while, it seems like that interval of convergence is not growing. We're going to talk about why that is. There are going to be some good reasons for that. Everything we do in Chapter 9 from here on out is going to be motivated essentially by what we just did. So let me just close you off with this question. This I think will be perfect timing. Why on earth would anyone be interested in representing something that's not a polynomial with a polynomial? Say again?
So you can solve it.
Why? Why would that help? Guys, this is the why, because we're about to go through some challenging things. It would be useful for you to know the why. Think. Liz said so you can solve stuff, right? Why?
Well, I know it would be easier to solve than straight functions.
Did you hear what Matt said? That's, guys, at its core, everything we're about to do in Chapter 9 is about that. Would you agree with me that polynomials are almost always easier to work with than things that are not polynomials? Would you guys agree with me that calculators and computers are much easier to program with polynomial-like things versus not polynomial-like things? So if I could take something that's not a polynomial and represent it with a polynomial, that would be good for programmers, mathematicians alike. That's what we're going to do. That makes sense? We'll dig into the details for the next 2 months or so. Okay? Have a great day. Glad you guys are here.